The Sharpe ratio is the most widely used number in finance, a single measure of reward per unit of risk. But the way we draw conclusions from it is usually wrong. Let's see how to do inference properly and the toolkit that follows. At its heart, the Sharpe ratio is simple: the mean excess return divided by the volatility. It is reward over risk, signal over noise. But we never observe the true values, so we plug in estimates from a sample of returns. That gives us a single number, a point estimate from finite data. And on its own, it tells us nothing about how much we can trust it. To trust that number, we need its sampling distribution. For over 20 years, finding a closed-form solution for its variance remained an open problem, one left stated but unsolved for realistic returns. The breakthrough of this paper is exactly that closed form, the variance of the Sharpe ratio when returns are non-normal and serially correlated. The variance splits into three interpretable pieces on top of the independent normal baseline: a term for serial correlation, a term for skewness, and a term for kurtosis. And it stays accurate even in small samples. Why does this matter? Take a 2-year monthly track record with realistic negative skew, fat tails, and autocorrelation. The estimated Sharpe ratio is 0.456. Under the honest distribution, its standard deviation is 0.379. But assume independent, normal returns, and you would report 0.214, about 43% smaller. In realistic cases, the true variance can be 4 times larger or more. Assuming normality does not simplify the problem, it manufactures false confidence. The fix is to report the Sharpe ratio in probability space. The probabilistic Sharpe ratio asks, given a benchmark, what is the probability that the true Sharpe ratio really clears it? It folds in the estimate, its standard error, and the higher moments of returns. For our example, against a benchmark of 0, that probability is 0.966. Raise the bar to 0.1, and it falls to 0.900. Same estimate, very different confidence. The same machinery answers a practical question. How long a track record do you actually need? The minimum track record length is the smallest sample that lets you reject the null with confidence. To beat a benchmark of 0 here takes about 19.5 months. To beat a benchmark of 0.1, it more than doubles to nearly 40 months. A higher bar demands far more data. Significance is only half the story. Power is the probability of detecting a truly good strategy when there is 1, the true positive rate. A test with too little power quietly misses real skill. In our example, with a genuine Sharpe ratio of 1/2, the chance of a miss is 41%. Assume normal returns, and you would think the miss rate is only 22%, underestimating it by nearly half. Always report power, so you know how much evidence your sample can actually deliver. Now flip the question. When you do reject the null, how often are you wrong? The planned false discovery rate is the probability that a rejected strategy is actually false. It is 1 minus precision. Suppose only 1 in 10 candidates is genuine. Even with a healthy 59% power, 43% of your rejections are false. When true strategies are rare, a passing test is far from a guarantee. This exposes a common mistake. The p-value is the probability of the data given the null, not the probability that the null is true. The observed false discovery rate gives you the second one. In our example, the p-value is a significant 3.4%. Yet the chance the strategy is really noise is 36%. Assume normal returns, and you would report only 16%, understating the risk by more than half. Researchers rarely test just one strategy. The false strategy theorem shows that if you try enough of them, a high Sharpe ratio will appear by pure luck. The deflated Sharpe ratio corrects for this by modeling the best of many trials, shifting the bar to account for the number of trials and how much they vary. After deflating our example across 10 trials, a probabilistic Sharpe of 0.97 collapses to 0.41, below a coin toss. Use it when one selected discovery has system-wide repercussions. Sometimes strategies are approved one at a time, meeting after meeting. The sequential false discovery rate sets a Sharpe ratio cutoff so that, among the strategies you approve, the chance of approving a false one stays below your tolerance. Here, controlling the false discovery rate at 25% requires a cutoff of 0.53, so our observed Sharpe of 0.456 is discarded. Use it when each decision carries only local repercussions. No single measure does everything. Each tool fits a stage of the investment process. In discovery, ask whether a pattern is signal or noise, using the probabilistic Sharpe ratio and power. In deflation, ask whether it survives the search, using minimum track record length, the observed false discovery rate, and the deflated Sharpe ratio. In validation, check that out-of-sample performance matches discovery. During allocation, control long-run error with the planned false discovery rate and sequential control. And in live trading and full deployment, keep watching the probabilistic Sharpe ratio and observed false discovery rate to catch alpha decay. So here is the new standard. A point estimate is meaningless without its sampling distribution. Report in probability space with the probabilistic Sharpe ratio. State the evidence you need through minimum track, record length, and power. Report posterior error with the planned and observed false discovery rates, not just p-values. And always deflate for multiple testing, choosing between the deflated Sharpe ratio and sequential control by the stakes of the decision. Do this, and the Sharpe ratio becomes what it should be, a tool for honest decisions.